Hey guys, Mr. Finn back in the lab for another episode of Finzics. Hey, I got a quick demonstration today regarding momentum. I've got my air track out. I know it's kind of long. I think you can barely see like the bumper here in the video, and then maybe right over here just outside the video segment is the other bumper. The bumpers are just rubber bands, okay? I've got another bumper on this glider with a rubber band on it, and this one doesn't have one. Now, I'm going to put these gliders on the track. This is an air track, so I've got a hose and a pump back here pumping air through the track, and air is going to come up through these little tiny holes all through the track, elevating these bumpers, elevating these carts rather. I'm going to send this car down the track, and I'm going to time it when it comes off the bumper. So I'm going to time it, and it looks like it's going to travel from about 174, and I'll set this one on about 100. So this one will travel about 74 centimeters. This one, when it goes, looks like it'll go down to about the 19 mark. So car A is going to travel about 74 centimeters. Car B, from 100 down to 19, be about 81 centimeters. Okay? No problem. But I'm going to use some masses, because the hard example for us in momentum is when a lighter car runs into the back of a bigger car. So we're going to put a lot of mass on this bigger car. Okay? Now, I measured these carts before we started. They were both about 180 grams. I'm going to add these masses. They look to be about 30 grams each. I'll measure those in just a minute. Okay, I'm going to put these masses on the car. I'm going to do the demonstration first. When I turn the jets on, this compressor on, it's going to be hard for you to hear me sometimes. So I'm going to time this one. It's going to hit. I'm going to time this one after. So I've got a watch that can do both things. Left click, right click to stop, and then I've got 2 times stored in there. I'll use a second stopwatch to time car B. So this is going to be kind of interesting for me. I'm going to time car 1 before the collision. After the collision, I'm going to mark a new distance. I'm going to stop this one down when it gets down to the end at 81 centimeters. Okay, so car A, car B, we're going to witness a bounce back. Okay, here we go, guys. Okay, this is going to be kind of a coordinating. I'm going to have to do a trial or two here. Okay, once again, smaller car running into the back of a bigger car. Okay, here we go. All right, I got my times. All right, now did you notice that the smaller car running into the back of the bigger car hits and bounces back? Bounces back. So if I had momentum this way in a positive direction, bouncing back would be a negative momentum. So this car originally has positive momentum. It's the only momentum in the system. Hits and bounces back. That was negative momentum after the collision. This car, positive momentum in its direction. Okay. So what I got here is this, guys. The black stopwatch, that was for car B. Time was 3.028 seconds. Remember, to go, it's 81 centimeters. I had 2 times on this one. I had 9.2 seconds. That was the bounce back. And I had 1.84 seconds. That was from the bumper to the collision. So what I'm going to do is I'm going to take this data and I'm going to go to the board and show you how this gets reconciled with momentum and the questions we can understand and get from there. Okay? All right, let's go to the board. Okay, guys, here to recap that example that we just did. So I took some measurements. I tried to take them as best I could. One guy here. Normally in Momentum Lab, we probably have 2 or 3 people, all with stopwatches and ready, and we would make sure that those watches were timed accurately and the distances were measured correctly. Okay, I did the best I could with one guy here, but you can see what we have. Car A, oops, that's mass A. Car A coming in with its 0.180 kilogram value at 0.40 meters per second. Hits car B, which is at rest, going this way. The net result is car A bounces back, car B moves forward. So here I have set P1 plus P2 equals P1 prime plus P2 prime. You can use P3, P4 if you want. You just got to make sure that you remember those masses are the same. Okay? All right. So now what do we got? Let's take a look. Mass 1, 0.18 kilograms times the 0.40 meters per second you had coming in. This is 0.378 kilograms, but it's 0. I always write it down anyway, even though we know we're going to go 0. So the total momentum before is contained in the first car. Now what happens after? That's where it gets interesting. Still got 0.18 kilograms here, but it's traveling at negative 0.08 meters per second. Yeah, that's slow, backwards. Plus the 0.378 kilograms times 0.25 meters per second. Okay, guys, so if you do some configuring here, this is going to be 0.072 kilogram meters per second equals, this is 0, this value is negative 0.014 kilogram meters per second. This value here is 0.095 kilogram meters per second with the numbers that I got. Well, you can see real clearly something doesn't look right. How did you get this momentum before the collision, and after the collision, one of those cars has more than the entire momentum before the collision? That's because of the bounce back, guys. This bounce back of car A after the collision means more momentum is imparted into car B than before the momentum to be even stand with. This is Newton's third law, has to hold, right? You have to have equal and opposite forces, so the accelerations must be proportional, inversely proportional to the masses. Okay, conservation of momentum says we've got about 0.081 kilogram meters per second afterwards, and over here 0.072 kilogram meters per second. So you can see my measurements were off a little bit, right? By a fraction of about, I don't know, a little bit less than 10% error in this experiment. So not that bad, but the key is to recognize the negative in the bounce back. It bounces back, goes back the same direction. Therefore, negative momentum after the collision ends, or after the collision takes place. So this one, a common physics question is something like, if car A runs into car B at rest and car A is lighter than car B, the total momentum of car B after the collision is less, more, or the same as car A before the collision. Very famous, and it's a bit of a trick. Car B, if you're just examining car B after the collision, it's more momentum than car A before the collision. Why? Because of the bounce back, car A is unable to impart, imparts more of the momentum because it maintains a negative value going in reverse. Okay, guys, I hope that works out. I'll do a couple more just to make sure you guys are all set, but that should lead you in the right direction. Remember, the bounce back is important. We've got to take care of direction in momentum equations.